And I'm back. So if we rearrange all of this, and let's say we divide n sub b from each side, then we have n sub a over n sub b, and then divide out sine theta a from each side, we're going to get Snell's law in a lot more useful format. So the angle, or the index of refraction and index of reflection comes into this neat little equation here. Now what's cool about this is we can also see that there's an equal sign here, so we can use this and figure that out. That's great. But let's say we aren't given the index of refraction. Instead, we're given a velocity. Well, the velocity that it travels through that medium is going to just equal this. And because it's an equal sign, then we could also say that the index n1 over n2 equals v2 over v1. And we can figure out the angle from there if that's what we need. So very useful format of this equation, and a relatively easy equation, I think. So good news there. On to some history. As I mentioned, the law is named after Willebrord Snellius, the Dutch mathematician and astronomer. The concepts go all the way back to Ptolemy in ancient Egypt. Ptolemy found the relationship regarding refraction angles, but it was inaccurate for angles that were not small. He was confident that he found an accurate empirical law, partially as a result of slightly altering his data to fit his theory. Don't ever do that. Alhazen, in his book of optics, came closer to discovering the law of refraction, though he did not ever actually take the step. The law that was eventually named after Snell was first accurately described by the Persian scientist Ibn Sahl at the Baghdad court in 984. In the manuscript on burning mirrors and lenses, Sahl used the law to derive lens shapes that focus light with no geometric aberrations. Stayed there for 600 years until it was picked up by Thomas Harriot, Johannes Kepler, and Willebrord himself. Here is a little visualization, a moving picture of refraction. You can see some of the rays are reflected, meanwhile some are refracted as it changes medium. This could be air to water, or less dense to a greater dense. When a ray passes from one material to another material, having a larger index of refraction, and hence a slower wave speed, the angle theta b with the normal is smaller in the second material than the angle theta a in the first. A ray entering a material of a larger index of refraction bends toward the normal. Just have that memorized. So if we're going from a small or a less small index of refraction towards a larger index of refraction, then it is going to be bent toward the normal. Ray entering material from a smaller index into a larger index is going to bend away from the normal. For reference, you just wanted to put on here the speed of light in a vacuum. We have c 3.0 times 10 to the 8 meters per second. So that way you don't ever have to memorize that, though it is useful and saves you some seconds. In the case of normal incidence, the transmitted ray is not bent at all. In this case, theta a equals 0, and sine theta a equals 0. So theta b is also equal to 0. The transmitted ray is also normal to the interface. The reflected index is also equal to 0, so the reflected ray travels back along the same path as the incident ray. Why does the ruler appear to be bent? Law of refraction explains why a partially submerged straight ruler appears bent. Light rays coming from below the surface change in direction at the air-water interface, so the rays appear to be coming from a position above their actual point of origin. So if we look at from the observer, the eye, we have, here's our boundary. Okay. So we have the incident ray coming in from the sunlight, hitting the ruler, coming back out, and now going from a larger dense to a less dense material. So it is bent away from the normal. For reference, some index of refraction for yellow light. Using yellow light, which is 589 nanometers. Let's see what we've got here. We've got ice is 1.309, water is 1.33. For air, we're always just going to use 1 because remember, index of refraction is the ratio of the speed of light in a vacuum to the speed of light in the medium. So if we're saying the speed of light in air is about 3.0 times 10 to the 8th meters per second, we get the ratio of exactly 1. Rock salt 1.54, diamond 2.417. An example problem. Light ray passes from air to water as shown. What are the change in wavelength and the light wave and the change in the angle of ray makes with the normal to the surface? If you don't have it yet, pause it now. All right, so here is the explanation. Frequency is going to stay the same when going from air to water. However, the speed will decrease. So the wavelength equals c over n times f, where n is your index of refraction. F is our frequency because that ratio. Therefore, the wavelength is inversely proportional to the refractive index of the material in which the wave is traveling. The refractive index for water is greater than air, so the wavelength is smaller. Meanwhile, when light passes from a less dense to a more dense substance, for example, from passing from air to water, light is refracted towards the normal. And if going from a more dense to a less dense, the light is refracted away from the normal. So there's your answer. Another one, let me try to get out of your way here. Let's see, I think that's good enough. A water wave entering a harbor suddenly passes from deep to shallow water. In deep water, the wave has a frequency of f1 and speed of v1. In the shallow water, the wave has frequency f2 and speed v2. Which of the following compares the frequencies and speeds of the wave between deep water and shallow water? Go ahead and pause the video here, try it for yourself. We know that C equals F lambda. Can't find my broom because that lambda kind of looks like a broom. The frequency is not changing. It's 4 waves per 4 seconds. If we imagine it's right here, second 1, right here, second 2, second 3, second 4, second 1, second 2, second 3, second 4. Still the same number of waves per second. However, the distance between the wavefronts does change. So it's a larger distance in the same amount of time. So that means we have a slower wave over here, whatever that means. So slower wave frequencies equal each other.